Okay, so we have what expression can be used to find the values of S of n in the table below. So we have these values n, which represent some numbers, and then S of n is some function. They did something to n to create these 5, 8, 11, and 14. Okay, so in looking at that, if I know I did something to n, right, and that's what all of these are doing. This is multiplying by 3, 5 times n plus 4, 3n plus 2. I think I would just check and see, can I do to one of these n's what they did and get the S of n value out. Okay, so look at this as being probably substitution method. Alright, so again, when I told you in an earlier video, I like to start in the middle of the table, and I'm kind of a sucker for the third one. Okay, so here if I say 3 times 3, I get 9, which is not equal to 11, which is what they said. So that is not what's going on here. Okay, and then 5 times 3 equals 15, which is also not equal to 11, which means that's not the pattern. Okay, n plus 4. N is 3. 3 plus 4 is 11. Sorry, 7, which is not equal to 11, so it's not C. And then on D we have 3 times 3 plus 2, which is 9 plus 2, or 11. So D is the pattern that is, or the function that is taking place here. Okay, let's take another look at another example. Hey, which algebraic expression best represents the relationship between a term in the sequence below and its position in the sequence? Okay, these are expressions which are very similar to our linear and quadratic equations that we've looked at in the previous problems. So the problem is I only have one variable, right? And I need 2 to make our table. So it says it's in relationship between the term, so this is my term, right, and its position in the sequence. Well, it's in the first position of my sequence. This one's in the second, third, fourth, fifth. So n is representing its position in the sequence, and then the term is the value we're getting out. So we again have a table of values, and I would probably select the middle term and see if it works in any of these problems. So 3 minus 1 is 2, which is not equal to 8. So that's not it. Okay, so this would be 3 squared minus 1, which is 9, minus 1, which is 8. So that one works. Okay, we can't call it the answer yet because we're just eliminating if it doesn't work. Okay, so 3 times 3 minus 1 is 9 minus 1. So it also gives us 8. And then 2 times 3 squared minus 2. So 3 squared again is 9. 9 times 2 is 18. Minus 2 is 16. So that is not equal to 8. So that one didn't work. So we can eliminate that. Alright, so let's try another point between G and H, because they shouldn't work for both. So let's try 4. So if we say 4 squared minus 1, that's 16 minus 1, which is 15. That worked. Then 3 times 4 minus 1 is 12 minus 1, which is 11, which doesn't work. So H didn't work for our second point. So G is the pattern that's happening there. Okay, not terrible. Let's move on. Which sequence uses the algebraic expression to describe the relationship between them? Okay, so this is sort of the reverse of the last problem, where they gave us one sequence and we picked the pattern. Now they've given us the pattern and which sequence would be generated. So it says n is its position in the sequence. So this is 1, 2, 3, 4, 5 positions. So I think the easiest thing to do here is just to find out what would be the resulting values. So So that's 4 plus 5 is 9. 8 plus 5 is 13. 12 plus 5 is 17. 16 plus 5 is 21. And 20 plus 5 is 25. Let's see, here at letter C, 9, 13, 17, 21, 25, they're a match, so I would select answer choice C here. Okay. All right, number 4, Mrs. Whittaker. Hey, I'm famous. Mrs. Whittaker used identical square tiles to design the 4 figures shown below. Which expression can be used to determine the number of square tiles used in each figure if n represents the number assigned to the figure? Okay, so here's figure 1, 2, 3, 4. So we already have our n's. Make a little T table here. 1, 2, 3, 4, and then the number of blocks or tiles. Okay, so that's 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, 6. Okay, so let's just try again. Like I said, I'm kind of a sucker for the third one, so we'll use n as 3. So for F, 3 times 3 would give us 9, which is not our 5. So it's not F. Okay, n squared, so 3 squared plus 2 would be 9 plus 2, which is 11, but it's not our 5. Okay, and then H would be 2 times 3 plus 1, which is 6 plus 1, which is 7. So again, not 5. And finally, n plus 2 is 3 plus 2, which is 5. Okay. Another way to look at that is, what did you notice here? We're adding one block, one more block, right? But because we started, and so that's that n is the number of blocks plus 2 more. We started with 3. If we went back here to 0, right, we would have still had 2 blocks. So that's where that 2 comes from. All right, number 5. Mr. Lyons invested some money that will double in value every 12 years. If he invested $5,000 on the day of his son's birth, how much will the investment be worth on his son's 60th birthday? Okay, so I looked at this one and said, okay, so the day of his birth, he's 0 years old, and he already has $5,000. Okay. And then when he's 12, the money doubled, so that means twice as much, or 10,000. Okay, and so when he turns 24, that'd be 20,000. And when he turns 36, that's 40,000. 48 would be 80,000. And then when he turns 60, well, that's going to be 160,000. So I like answer choice B. All right, number 6. The table below shows the number of sides and diagonals in certain polygons. Based on the table, how many diagonals should a 9-sided convex polygon have? All right, well, when we went up 1 on the number of sides, we increased the diagonals by 2, and then we increased by 3, and then we increased by 4. So it seems like we're increasing 1 more each time. So I could continue to carry the pattern out that way. That might be, it's not too bad. We're only going to 9. So I think that may be what I do. So it's 7, 8, 9. I would increase by 5 here. So 9 plus 5 is 14. And then I would increase by 6, which is 20. And then I would increase by 7, which is 27. So I would expect to have 27 diagonals if I had a 9-sided convex polygon. All right, that's it for this lesson. Good job, guys.